Hello friends, this is Jim with Science Talk. I have some news from the world of oceans. New ocean current discovered off the coast of Madagascar. A previously unknown ocean current was recently discovered off the coast of Madagascar, which is rare in this day and age. The new found, and it's being called the Southwest Madagascar Coastal Current, could help researchers better predict the effects of climate change. Ocean currents are part of a huge giant circulation system that moves water, nutrients, and heat around the globe. Now, sailors have long known of what they sometimes call oceanic conveyor belt, these ribbons, quote unquote, in the sea that they can get in the current, and the current will transport them to a desired location that they're headed to. The first truly systematic description of global currents was published in The Physical Geography of the Sea, Harper and Brothers, in 1855 by Matthew Fontaine Maury, who at the time was the head of the U.S. Navy Depot of Charts and Instruments. Maury not only compiled data on current direction and strength using sailors' logbooks, but he also discovered new currents by tossing messages in bottles out to sea, then tracking where they wound up. So the old cliche of tossing a message in a bottle, well, there is some validity to that. So, back to this Southwest Madagascar coastal current. Marjolaine Krug, who is the study co-author and researcher at the Council for Scientific and Industrial Research in South Africa, said, "I think we've discovered most of the major currents. One of the reasons why this one was not known is that the region has been very much undersampled." If you can't take samples, you're not going to find what's there, right? The Southwest Madagascar coastal current was a missing piece in scientists' understanding of the world's climate. The team, which consisted of South African, Malagasy, and French researchers, was investigating the strip of ocean between Mozambique and Madagascar, known as the Mozambique Channel. They noticed that there was water coming into the channel that could not be explained by other known flow sources. They then looked at satellite imagery, and then they discovered a completely new current carrying water along the Madagascar coast and then toward Earth's poles. In oceanic terms, the Southwest Madagascar coastal current is fairly small. It is only 62 miles long. It's only 330 yards deep, about 300 meters, and it transports about 264 million gallons, 1.3 gigaliters of warm, salty water a second. Okay. Now, there is a term that we use in oceanography to denote water transport, and it's called a sverdrup, which is spelled S-V-E-R-D-R-U-P, named after the Norwegian scientist, and typically that's 10 to the 6 cubic meters per second of water. So that's pretty much reserved for very large currents. But a sverdrup is a standard unit to denote water transport in the oceans. It's not so much the size of the current, but its location that makes it vital to understand its relation to the world's oceans and climate and other flow patterns. The Mozambique Channel feeds the Agulhas Current, one of the strongest currents in the world. The Agulhas Current affects the path of tropical storms and carries heat toward higher latitudes. Now, the Agulhas Current is a strong current that, basically in the Indian Ocean that flows southwest around the southern portion of Africa. And the Agulhas current posed challenges to Portuguese sailors circumnavigating Africa to get to India because it's a very hard current to go upstream against. The Agulhas is the equivalent of the Gulf Stream, but for the southern hemisphere, Professor Krug added. So understanding the sources of this Agulhas current could help scientists better predict the effects of climate change. The study was published in the journal Geophysical Research Letters. So that's very interesting because, and look for me to be doing some videos about the Atlantic Meridional Overturn Circulation, or AMOC as it's called. There's some very interesting developments going on with that, and basically a little bit of a spoiler alert, it's slowing down. And in upcoming videos I will explain what this is all about, the slowdown of the AMOC. So look for that video coming up in the next week or so. Here's another story involving oceans. Apparently oceans can create magnetic field. And the magnetic field of the ocean was mapped in very excellent detail from space. Satellites circling Earth have mapped an elusive, invisible force in unprecedented detail, the magnetic field created by the currents in the planet's salty oceans. Now, most people are familiar with the magnetic field produced by the Earth's molten iron core, but there's also a field generated by the oceans. So, what took place here? The European Space Agency directed 3 identical spacecraft, which were launched in 2013, and they collectively call them SWARM, to map the magnetic field emanating from the ocean's tides. The new research, as well as the digital 3D map that it helped create, is providing new insight into how this magnetic field is generated, as well as how it behaves and changes over time. The magnetic field as produced by the oceans, the molten core, and rocks in the crust and upper mantle protects the planets from streams of particles known as the solar wind and sometimes the cosmic rays. So we all know about the molten core, the molten iron core of Earth that produces a magnetic field, very strong magnetic field, which deflects the incoming solar wind. Apparently, the magnetic field produced from the salt content in the ocean adds a very small contribution to this as well. So, what did researchers do? They had these satellites, they mapped the ocean's contribution to the magnetic field, and they got excellent precision. The researchers chose to focus on the oceans because they make a tiny but important contribution to the Earth's overall magnetic field. The salt within seawater can conduct electricity. Very basic experiment. Get a thing of fresh water, potable water, stick a couple of electrodes in it, hook it up to a battery, and hook it up to a source. Nothing will happen when you say turn the switch on. Add salt to that water and you get a current, and that, if say you hooked up to a little basic bulb, the bulb will light up. So salt water is conductive. It will conduct electricity. And of course we all know that oceans don't just sit still, they're moving about. There's currents, there's tides move in cycles, up, down, ebbing, incoming, and so forth. As the tides cycle through the world's ocean, that salty water essentially tugs on the magnetic field above our planet. So the researchers used SWARM to measure the magnetic signals of tides from the ocean surface to the seabed, and that gives a very good global picture of how the ocean flows at all depths. And this is new information. This was said by Niels Olsen, who's the head of geomagnetism at the Technical University of Denmark. The magnetic field generated by the ocean is small. It's about 2 to 2.5 nanotesla at satellite altitude, which is about 20,000 times weaker than the Earth's global magnetic field. The newly analyzed data will give researchers a more nuanced view of how the oceans are affected by climate change. Since oceans absorb heat from the air, tracking how this heat is being distributed and stored, particularly at depth, is important for understanding our changing climate. Moreover, the tidal magnetic signal in turn induces a weak magnetic response from deep under the seabed, Professor Olson added. The new research is under peer review and should be published shortly once revisions are made, and then it is accepted. Now what's interesting is the part about the oceans absorbing heat. You may recall I did a video a short while ago about the global warming pause, and basically not so fast. It turned out that a lot of the heat was actually absorbed by the ocean. So it didn't just stay in the atmosphere, but it started to be absorbed by the ocean, and the ocean absorbed a lot of it. A lot of the heat, as it turns out, has been being absorbed by the ocean. Water has a much higher specific capacity than air, which means what? It takes more energy to heat up the same. If I have a given quantity of water and the same given quantity of air, it takes a lot more energy to raise this volume of water, say 1 degree Celsius, than it would this same volume of air. So for the water to absorb all that heat, that means it's absorbing a lot of energy that's the result of burning a fossil fuel. So increasing ocean temperature by 1 degree C requires much more energy than increasing the atmosphere by 1 degree C. And of course, with that, with the increase in heat in the ocean, you have thermal expansion. You heat something up and it expands. So that is one contributor to rising sea levels, in addition to glacial melt, land-based glacial melt like Greenland, Antarctica, glaciers in the Alps and the Rockies and Alaska and so on, Andes, etc. So we have two mechanisms by which sea levels will rise: melting of land-based glaciers, thermal expansion in addition of the water. So, and then there's another issue. When you heat up the upper layers of the water, you create a stratification. And that stratification can prove to be a barrier to trying to mix any nutrients from deeper in the water column up into what's called the photic zone. The photic zone is that layer of the ocean where light penetrates so that phytoplankton can then utilize the light energy to, along with combination of CO2 and water, can undergo photosynthesis, make glucose, etc. So, but the phytoplankton need what's called micronutrients like iron and other trace elements. If those elements cannot be brought up into the photic zone, even though there may be plenty of CO2 and water around, they're not going to be able to photosynthesize effectively, if at all. So there are several ramifications, all of which are not good, for heating up the ocean. But I thought this is a new information for me, learning of a magnetic field from the ocean. It does make sense when one stops and thinks about it that salt water will conduct a weak electrical current, and if you have electrical current, typically you have a magnetic field associated with it. For example, power lines, right? There is a magnetic field. You have the current flowing down the line, but there is a magnetic field that is created by that current that's flowing in the wires. Typically, such magnetic fields are what we call orthogonal, or 90 degrees to the main directional flow of the electricity. Be that as it may, but this does make sense, and now they have actual measurements of that, and that to me is the really interesting part of this. If you like this video, please share, please subscribe, hit the bell so that you know when a new video has been added by myself. I hope you'll consider supporting my work. Go to patreon.com/Science Talk with Jim Massa. Become a patron. If you're already a patron, thank you for your support. Please share this video, and we'll talk to you soon.